Welcome back to Physics After Hours. We will call this Unit 1 Test Solutions Part 2. All right. So I've zoomed in the camera a little bit to hopefully improve the resolution and make it a little easier to read. I hope this has fixed the problem. So moving on with the test, we're on problem 6 here. We've got an electron moving along the x-axis with a position given by x equals 14t squared plus 5t plus 20. The problem asks, at what time in the future does electron momentarily stop? Okay, so what does that mean, momentarily stop? Well, if something stops for a moment, its velocity then equals 0. So we must find t when velocity equals 0. What is velocity? Well, velocity is the rate of change of the position up here, which means the derivative of x with respect to t, or the derivative with respect to t of 14t squared plus 5t plus 20. All right? Well, if we differentiate each one of these part by part, I guess if I want to do it in very nauseating detail, d dt of 14t squared plus d dt of 5t plus derivative with respect to time of 20. Well, the derivative of this, if you remember from the power rule, is 14 times 2t to the 2 minus 1. Plus the derivative of this is 5 times 1t times raised to the power of 1 minus 1. Okay? Plus 0. The derivative of a constant is 0. And I told you you'll have to trust me on that. Simplifying this, 14 times 2 is 28. T to the 2 minus 1 is t. And 5 times 1 to the t to the 1 minus 1, that's the same as t0, which just equals 1. Anything raised to the 0th power equals 1. So that is plus 5. So velocity is 28t plus 5. That is the velocity function. How does velocity change with time? So the question wants us to find when the electron momentarily stops, so we know all of this must be set to 0. And then we'll find the time when this happens. So if I subtract 5 from each side, 28t equals negative 5, and divide each side by 28, t equals negative 5 over 28. That's your answer. Now, some very astute people who saw this on the test also read very closely where I said, at what time in the future does the electron momentarily stop? This time is negative, and this is the singular solution of this problem. So what does that mean? It never, the electron never stops in the future. That was a very astute observation. Congratulations if you noticed that. If you didn't notice that, I just gave you full credit for t equals negative 5 over 25. Okay? What does it actually mean if you get a negative time? Well, if you have this is x, and you have some quadratic, so it's going to look something like, I don't know. This is not this particular function. This is just some function. Go with me on that. So this is the function x of t. At what time does its velocity equal 0? Well, we found the derivative, which is going to give the slope at any point in time. So at some point, the slope is down here at negative 5 over 28. So the velocity is 0 some point before the origin. Well, where you choose the origin is arbitrary. We could have chosen the origin out there, and then we would have to define our function differently. But this is how the function was set up, and so you've ended up with a negative time because of that. Okay? Question 7. A rock is thrown straight up with an initial velocity of 10 meters per second. I'm going to circle that. V0. And I'm also probably going to say circle straight up. What time interval t elapses between the rocks being thrown and its return to the original launch point? Okay, so draw your diagram or your sketch. Rock goes up, rock comes down. And this is negative V0 over here. I'm going to call this Y. And this is, well, it's Y0, and it's also Y because we're going to the original launch point. So writing this down, we call Y0, 0. Because why do you do that? Well, you can define the origin anywhere, but we normally always want to find something as 0 because it makes the math easier. A term drops out. So we, of course, choose y0 to equal 0, but we know that it returns to the original launch point, so we can also choose y as equal to 0. Well, Vy0 is equal to plus 10 meters per second, and here's the tricky part. We also know that Vy is equal to negative Vy0, which is equal to negative 10 meters per second. This is just a matter of symmetry. No force is acting on it in this trip, so we know you throw it up, it goes with some velocity, it slows down until it stops at this point, then it starts speeding up again over the same path length, and so at the end it's going to have the same magnitude of velocity as it had in the beginning, different directions. However, you're going to see we don't even need this to solve the problem. So if you didn't identify this and you solved the problem the way I'm going to do it, I didn't take off points for that. The acceleration, again, is always negative 9.8 meters per second for projectiles, and t is equal to ty. It's kind of a formality. For x, all this stuff equals 0. Acceleration, of course, equals 0. That's an important part. And the t just equals tx. If you just wanted to put an x through that, that would be fine. Okay, so looking at our equations, here they are. Running out of room. I need an equation. Again, this is in the x direction, but it doesn't have to be. We can just swap out the subscripts, x for y, because these relationships hold no matter what dimension you're working in. So we have y0 and y, they both zero out, so that means this would zero out, and we're looking for time. This equation has time. We have the original velocity, we can do that. We have the acceleration. We can use this equation. We cannot use this equation right now because could we? Yeah, you could use that equation, sure. Then you would just have to recognize that the final velocity is the negative of the original velocity. Sure, you could use that equation. What about this one? Well, this one doesn't contain time, so that would be kind of difficult to find that. In this case, the change in y is going to be 0, so you would end up with 0 equals 0, so that equation's not going to get you anywhere. Let's just go with the second equation. I'll erase that so I can use this paper later. So y minus y0 equals v0y times time plus 1/2 AYT squared. We know that equals 0. We know that equals 0. We have this. We can solve for time. v0yt plus 1/2 yt squared. I can factor out a t from every term here, v0y plus 1/2 ayt. So at this point, you have two t's here. You're going to have two solutions. One solution is t equals 0, which is not really a solution to our problem because we want to know how, not at the beginning of the time span. We want to know how much time elapses until it comes back down. So we'll not look at this formula. We would just look at the solution v0y plus 1/2 ayt equals 0. And the reason I say there are two solutions because either this part has to equal 0, in which case it doesn't matter what this is, or this part has to equal 0, in which case it doesn't matter what t is. One of these two things has to equal 0. This equals 0, or this whole thing here equals 0. Either one will get you to the point on the left side of the equation. Well, what if you don't really think that way? Well, there's another way to think about it too. You can just say, I'm going to divide each side by time. 0 divided by t is 0, and t divided by t is 1. So 1 times v 0y plus 1/2 ayt definitely is going to be equal to 0. So if I'm going to solve this, I'm going to subtract v0y from each side of the equation. 1/2 ayt equals negative v0y. And ayt equals negative 2 v0y. All I did was multiply each side by 2. So 2 times 1/2 is 1, of course, so this goes away. And 2 times negative v0 is right there. Divide each side by ay. T equals negative 2 v0y over ay, which just equals negative 2 times 10 meters per second over negative 9.8 meters per second squared. Time equals, I believe it was 2.04 seconds. There is another way you could do it. Like I was mentioning earlier, you could use this equation, this first equation here. So Vy equals V0y plus AYT. Well, we know from back here in our chart that Vy equals negative V0y. So I'm going to put in negative V0y in there, which is going to give me negative V0y equals V0y plus AYT. Okay, when I subtract V0y from each side, I get negative 2 V0y equals AYT. And if I divide each side by AY, and I'm just flipping the equation, I hope that's not a problem, T equals negative 2 V0y over AY. So you see, that is equivalent. Two ways of working the same problem. Now there is a completely different way to work this problem, and I'm going to show you just for completeness, so that you see all ways to work it. If it's too confusing to see 3 methods to solve the same problem, just go ahead, skip to the next video. Well, not the next video, the next problem. Excuse me. All right, so in this case, we draw my diagram again. Plus V0y. But in this case, I'm not going to look at the return. All I'm going to do is look at the point up to here where Vy equals 0. That's the peak of the path. And as usual, this is y0, and this is y. We don't know what y is right now. I'm going to list everything. y0 equals 0, y equals, we don't know, v0y equals 10 meters per second, vy equals 0, ay equals negative 9.8 meters per second squared, t equals, we don't know. All right, I'm looking for my equations. Here we are. So I need to somehow get time from this information. Well, we can just use that equation again, right? So Vy equals V0y plus AYT. We said that Vy is going to equal 0, so negative V0y, negative V0y, AYT, that those cancel. So negative V0y over AY equals T. If you notice, this is exactly 1/2 of what it is over here. See that extra factor of 2 there? We don't have that over here. That is because we found the time it takes to go up and stop. We didn't find the time to come back down, but we know there's one constant acceleration operating on the whole thing. So if we call this T1, T2, we can say T1 equals T2, and T then just equals 2T, T1. So I'm going to go back and label this T1 everywhere. Make sense? So if we then solve for the total time, we have to multiply everything by 2. Which then is exactly equivalent to our previous solutions.